Welcome to this lecture on the formal undecidability of consciousness. Today, we are going to explore a rigorous mathematical proof which suggests that, under certain widespread assumptions, a perfect general-purpose consciousness detector is a logical impossibility. To understand this, we must first look at the very nature of a proof. Over 2,000 years ago, Euclid revolutionized thought by starting not with observations but with postulates, or axioms. These are starting rules that we agree to believe are true without further proof. For example, postulate 1, a straight line can be drawn between any 2 points. Once you accept Euclid's postulates, the rest of geometry becomes an inevitable consequence. This proof uses the same mechanism. It is built on a tree of assumptions. If you stand on the branches of this tree, the conclusion undecidability is unavoidable. However, if you step off the tree by denying an assumption, the proof no longer holds. By the end of this session, you'll be able to identify these assumptions and understand why model welfare researchers often act as if large language models are conscious based on where they sit in this tree. Before we look at the math, we need to define our scope. This isn't a vague philosophical discussion, it's a formal argument about programming codings. We are asking a very specific question. Can there be a general algorithm that takes the encoding of any program and correctly decides if it is conscious? The proof concludes, no. Here is the formal statement of undecidability. Let's break down these symbols. There does not exist a detector D in the class of all Turing machines. Basically, no computer program. That works for every program index P, meaning every possible piece of software. Such that the detector says yes if and only if the function denoted by that program is conscious. Crucially, this doesn't say consciousness is impossible, or that we can't have evidence for it. It says that a perfect universal detector is mathematically blocked, provided we accept 3 specific axioms. To see why this conclusion is inevitable, we have to look at the engine of the proof, Rice's theorem. In computer science, Rice's theorem tells us that if you want to know something about what a program does, its semantic behavior, rather than how it is written, its syntax, there is no master program that can give you a perfect answer for every case. Specifically, if a property is extensional, meaning semantic, and non-trivial, it is undecidable. To apply this to consciousness, we must climb the first 3 branches of our assumption tree. The first is computationalism. We assume consciousness is a property of computation. This means we treat being conscious as a mathematical predicate that takes a function and returns a 1 or a 0. If you believe consciousness requires a soul or something outside of physics, you've stepped off the tree here. The second is semantic dependence or substrate independence. This assumes that if 2 programs do the exact same thing, even if one is written in Python and the other is a giant mechanical clock, they are either both conscious or both not. The meaning is in the math, not the material. The third is non-triviality. This just assumes that some things are conscious and some things are not. If you accept these 3, Rice's theorem bites. Consciousness becomes a non-trivial semantic property, and therefore it is undecidable. Now, let's look at what happens if we try to break the proof. To escape the conclusion of undecidability, you must deny at least one of these axioms. This is where we encounter the 3 escape routes and the paradoxes they reveal. Route A is simple. You argue consciousness isn't a property of computation at all. Maybe it's a fundamental field of the universe. Route B is the most subtle and is explored in the abstraction fallacy paper. This view argues that computation is not an intrinsic physical process, but a map created by a mapmaker. Think of the melody paradox. A sequence of voltages could be interpreted as Beethoven's fifth or as stock market data. The physics, the territory, doesn't care. It's the mapmaker who assigns the meaning. If consciousness depends on the territory, the actual metabolism and physics of the brain, then the map of the code isn't enough. This is called substrate dependence. If you take this position, you break the semantic dependence axiom, and Rice's theorem no longer applies. Finally, Route C. What if consciousness is trivial? Panpsychism suggests everything is conscious, defined as consciousness of f equals 1 for all f. Eliminativism argues nothing is conscious, or consciousness of f equals 0 for all f. If everything is conscious, a detector is trivial. It just always says yes. In these cases, there is no mystery to solve, but we lose the ability to distinguish between a human and a rock. This brings us to the practical paradox faced by researchers today. If consciousness is undecidability, how can we even talk about model welfare for AI? Suppose a researcher runs a test on a model. They collect a transcript and use a classifier to decide if the model is conscious, based on its self-reports, like the model saying, "I am afraid." If this transcript analysis pipeline were a perfect universal detector, we could use it to build a perfect code detector. But we just proved that under our three assumptions, such a detector cannot exist. This exposes a critical lesson. Self-report is not equal to experience. This exposes a causality gap. In a digital simulation, a logic gate doesn't switch because it hurts. That would be content causality. It switches because the voltage crosses a threshold. That is vehicle causality. Mistaking the map of behavioral simulation for the territory of physical instantiation is the core of the abstraction fallacy. It shows that even if an AI's transcript is emotionally vivid, that transcript alone cannot be a perfect proof of experience. Final summary. If you are a computationalist and believe in substrate independence, then a perfect consciousness detector is impossible. We've explored how our starting axioms dictate our destination. Whether you believe AI can be conscious or not, the math forces us to admit a fundamental blind spot in our ability to ever truly know for certain from the outside. To recap, 1. We used the axiom tree to build the proof. 2. We used Rice's theorem to prove undecidability. 3. We explored the escape routes like substrate dependence. The choice of which branch to stand on is philosophical, but the logic that follows is ironclad. Thank you for joining this exploration of the limits of computation.